Okay, so these are the discussions that we had in our April 2025 physics lessons. Remember, you can find me at number 1572 Freedom Street, Highway, Glendale, or Umuzi Church of Christ. So here we are talking about the acceleration of it. So this happens in a vacuum, in an empty space where there's no air. So when something is falling down in a vacuum, the only force that would be acting on the object would be its weight. Remember Newton's second law, F is equal to ma, so the force is going to be the weight here, which is equal to its mass times acceleration due to gravity. And remember that on Earth, all objects which fall downwards experience an acceleration of about 10 meters per square second due to gravitational pull, and this acceleration is called gravitational acceleration, denoted g, which is equal to 10 meters per square second on average. So this gravitational acceleration is independent of the size, shape, or mass of the object. Hence, if we didn't have any air, if we had a vacuum on Earth, then whether a feather or a hammer, whether you had a feather or a hammer falling from the same point going downwards, it would reach the ground at the same time. That is in a vacuum where there is no air resistance. However, here, any object that moves in air, we experience a force called air resistance. So Earth is not a vacuum, we have air, so there's going to be air resistance, which tends to slow down the motion of objects that are falling. So this is why here on Earth, when you throw a hammer and a feather from the same distance, from the same height, they are not going to reach the ground at the same time. Why? Because there is now air resistance, and this force is, we're going to look at the factors that influence this force. So here, air resistance is proportional to, number one, the contact surface area between air and the object, and the speed of the object. So the surface area, the contact surface area between air and the object. So you can imagine for the hammer, for the nail, there's going to be different contact surface area. So, and then the speed of the object. So when the speed of a falling object increases, air resistance will increase as well. So you need to know that this is directly proportional to the speed of the falling object. When it increases, air resistance will also increase. So when air resistance equals the weight, this is important. When air resistance now equals the weight of the falling object, the net force is zero. So remember, what's happening here is that your object is falling downwards due to gravitational pull, and air resistance is going in the opposite direction. So you have when these forces are not equal, you have a net force which is not equal to zero. But when these forces are now equal, then the net force is going to be equal to zero. Hence, the object reaches terminal velocity and stops accelerating. So when these forces are now equal, then your object no longer accelerates. Remember, when it's falling downwards, the acceleration is the speed, the velocity increases. So there comes a time when your air resistance is equal to the weight, and hence the net force becomes zero, and there is no net acceleration. There's no acceleration. So let's look at this in detail here. So we are saying here the falling object with a mass of m experiences this force pulling it downwards. W is equal to mass times acceleration due to gravity. And there's air resistance here. We are going to use R to represent air resistance, which is acting in the opposite direction to that object. And we said here the resultant force here, if your weight is greater than the air resistance, then the resultant force is going to be going downwards. So when we show this on a graph, this is what we see. So between here 0 and t1, when you have a straight line here, this is your velocity time graph. Remember, when you have a straight line, if you still remember, you can go back if you have forgotten this. that what is the meaning of having a straight line here. So what this means is that our air resistance here is 0 here. The resultant force is F, which is given by the mass of the object times acceleration due to gravity. So what does this mean for our acceleration? Our acceleration is equal to G, which is acceleration due to gravity. But here we start to see our curve starting to face downwards. So something is starting to happen here between T1 and T2. What happens? So our air resistance now increases. Our air resistance increases, and our force, the resultant force, is now equal to the mg minus the air resistance, and our acceleration in that case starts to go below g. So acceleration is now less than g. So there's a deceleration there that is happening in this region, T1 and T2. And now above T2 we start to see a straight line here. What does this mean? It means that our object has reached its terminal velocity. And now our r is equal to mg. The air resistance now equals the weight of this object. So these two forces, this one and this one, are now equal. What does this mean to our resultant force? The resultant force is now equal to 0, and our acceleration is now equal to 0. So the object is no longer accelerating when it reaches this terminal velocity. So this is what happens due to air resistance when something is falling on Earth. So I'll meet you in next videos where we are going to be looking at calculations using SUVAT equations. If you join our groups, if you join our online lessons, we'll be throwing in a lot of exercises, a lot of calculations, so that you're familiar with manipulating these the different formulae that we looked at. So I'll meet you in our next episode of April holiday lessons. If you're in Glendale, you can always join me online. I'll be available online if you need further assistance. If you'd like to join us for physical lessons, contact me for further details. We're at number 1572 Freedom Street Highway, Glendale, or at Umuzi Farm, Glendale Church of Christ. So I'll see you there.